Hello, everyone, and welcome to the final session of Porous Media Tea Time Talk. It's the last session of this year, but we'll be back early next year with a new season or new edition of PMTT. First of all, on the behalf of the organizing committee, I would like to thank all of our speakers and audience for making it a great experience. And hopefully, everyone has found it useful. And I think a nice way to connect with researchers from Porous Media community. I would also like to thank the Intropore organization for the help in promoting and highlighting our webinar series. And I would also like to mention that this series is aligned with the Geoscience and Geoenergy webinar series, which is hosted by Sebastian Hardy. You can find further details in our featured channel. As you can see from the labels of our video, my name is Kamaljeet Singh. And today in our studio, we have Catherine Spurn and Mohammad Nuraipur, Maya Rukar. Unfortunately, Marcel and Tom couldn't join us today. I'll pass on to Catherine for chairing the first session.
Thank you. So our first speaker today is Mehrdad, who did his BSc in Amir Kabir University of Technology in Iran and his MSc in the Technical University of Denmark. He started his PhD at ETH Zurich with a focus on visualization of pore-scale processes in 3D printed porous media, and he defended his PhD just a couple of weeks ago. So congratulations for him for successfully achieving his PhD. This project is motivated by EGS, which is the Enhanced Geothermal System that aims at filling the knowledge gap in pore-scale processes. So I shall pass over to Mehrdad now.
Thank you so much, Catherine, for the introduction, and I would like to thank everyone for joining my presentation today, and also the Porous Media Tea Time Organizing Committee. It's a great pleasure to be here to present my work, which is a part of the work that I've done during my PhD at ETH Zurich. Today, as the title explains, I'm going to talk about the experimental part of my study, where we tried to visualize fluid flow and solute transport in fractured porous media. So in subsurface applications, with the motivation, of course, in subsurface applications, pore-scale properties, fluid flow and solute transport has been studied in different scales, changing from nanometer scale to kilometer scales, where there is a hierarchy of information. Our understanding of smaller scales can shed light on our understanding of larger scales. Here, of course, we are interested in the pore scale, which changes from few micrometers to few centimeters. Pore scale has been a very attractive field of research because of its wide range of applications in different industries. There are various numerical simulation methods and experimental methods as well. For the sake of time, of course, I can't go through all of them, but I want to point out some commonly employed porous media which are used for experiments, which can be, for example, core plugs or randomly packed bits. Although these geometries have contributed a lot to our understanding of pore scale properties, they're associated with some limitations. For example, experiments sometimes can't be replicated. The complexity is random, it can be engineered, and especially for randomly packed bits, the manufacturing of fractured porous media is sometimes limited. But with the recent advances of 3D printing, researchers are capable of addressing some of these shortcomings. There are plenty of very interesting studies where pore scale properties in structured and unstructured medium have been studied. However, fractured porous media, we believe that require more attention. It has not been studied enough, and that's the reason that we use 3D printing to manufacture a fractured porous media. Our medium consisted of a low permeability matrix and a high permeability matrix, which are constructed by an isotropic distribution of impermeable pillars. As you can see here, the permeability of these matrices are based on the pore sizes, which is the spacing between these impermeable pillars. inside each of these uh, matrices, we embed one dead-end fracture and one flow-through fracture. And once we could make and manufacture our 3D printed fractured porous media, we conducted two sets of fluid flow visualization experiments, which are magnetic resonance imaging, MRI, and particle image velocimetry, PIV experiments. For the sake of time, I'm not going through the technicalities. We can, of course, discuss it in the QA session. But as you can see, both of them are capable of visualizing fluid flow. As we expected, velocity is higher in fractures and especially in flow-through fractures. And then both experiments are in good agreement, although there are some discrepancies in the especially higher velocity regions. Here, I want to especially show the PIV, particle image velocimetry, because of its high resolution, where we could first of all visualize velocity in the entire domain. But thanks to our very well defined geometry, we can look into different features individually. For example, we can study flow pore scale properties here, velocity in flow through fractures and dead-end fractures. And then thanks to our high resolution, we can go more detailed and look at, for example, the interfacial behavior between fractures and matrices, as well as the flow velocity inside the porous media. When after visualizing fluid flow, we studied what we call hydraulic boundary conditions. And the application of hydraulic boundary condition is for coupling of flow in fractures and in matrices. In fractures, we solve fluid flow with normally Navier-Stokes or Stokes equation. In matrices, of course, it's Darcy's equation. Coupling of these two equations at the interface can be very complex. And that's why two different boundary conditions are proposed. Here we're going to talk about two well-known ones, which are Beavers and Joseph velocity slip coefficient alpha, and then Whittaker coefficient beta, where they are calculated by the permeability of matrices, the shear rate inside fracture, and also the shear rate inside matrices, as well as the velocity at the interface. And here is a magnified image. On the right, we have our fracture part. On the left, we have our matrices. And here, these blue squares are our impermeable pillars. And you can see how the velocity profile looks at the interface. We then could calculate alpha and beta with the presented scheme for all the four fractures. Each fracture has two interfaces with the surrounding matrices. So we could calculate alpha and beta for 8 interfaces. And on top of that, we were able to directly measure velocity exchange between the fractures and matrices, which is based on the lateral velocity perpendicular to the flow direction, velocity exactly at the interface. We believe that these measurements can be used in validation of numerical simulations and can contribute to our understanding of the coupling between fractures and matrices. With that, we started another round of experiments where we studied solute transport with laser-induced fluorescence, LIF experiment. In these experiments, we could inject either tracer dyes or deionized water into our fractured porous medium. We illuminate the system with a laser source and then capture images with our camera. These tracer dyes get excited by absorbing the laser, and then they jump back to a lower energy level, which emits a light with a different color and with a lower energy. And the emission of the intensity of this emission depends on various factors, such as laser power, for example, or quantum yield. But what's important here, which is also a variable, is the concentration. So we are able to link the light intensity with concentration in our LIF experiments. And that's these are how just some videos of how our experiments look like. In the progression, we start injecting tracer dyes into our medium, which is initially saturated with the ionized water. Afterwards, once the system becomes fully saturated, we start injecting the ionized water again to displace the tracer dyes. You can see how the light intensity changes, which is an indication of tracer concentration. In all these experiments, the idea of having a well-defined geometry was to be able to make conclusions quantitatively and qualitatively, meaning that here, quantitatively, we calculate standard deviation of tracer dyes in flow and perpendicular to flow direction, and then we could see how the decrease of the standard deviation is related to a qualitative evolution of concentration in fractures, in dead-end fractures, and in the later stages. And yes, I think I'm going slightly over time. So with this, I want to conclude my presentations, where we could combine 3D printing with MRI and PIV for fluid flow visualization, and 3D printing with LIF for visualization of solute transport. Thank you so much for your time and attention, and I will be glad to for questions. Thank you.
Thank you very much for the great presentation. The presentation is now open for discussion. You can always post a comment in our comment section. So if you have any questions, please write it down there and we will read it then to the speaker. In the meantime, I actually have a few questions. So sure. maybe I just start with the first one being, you mentioned at the beginning about the effect of molecular process. The problem is a multiscale problem, and that also molecular interactions may matter. To which extent is this the case? Or how do you think this impacts also when you construct a model with 3D printing?
To me, here, when we are talking about scale, it's mainly about the resolution at which we are resolving our properties. So it's either we get our measurements in nanometer scale or micrometer scale or kilometer scale. Since our measurements and our geometry in general ranges between a few micrometers to centimeters, then this is more of a porous scale, and then it's not really a molecular scale problem, I believe.
Okay, thanks. But I think this is also directly leading to the first question which we have from our audience, which is from Vita P. Thanks for the nice talk. What is the smallest pore that was printed? Lowest diameter, for example.
Yes. So here the smallest pore that we have is 200 microns or 0.2 millimeters, which is the spacing between two square pillars in the low permeability matrix. And the width or the depth of the geometry is also 300 micron or 0.3 millimeter.
Is it the resolution with which you can get with a printer, or did you choose them for a specific reason?
It was to a large extent because of the technical limitation. By the time that we wanted to print our geometry, we couldn't go any smaller with the resolution. I think, or from what I've read, now there are other 3D printing methods which are capable of printing smaller scale pores. But we should always have in mind the overall size. So, for example, if it's really advanced techniques, we can maybe make pores up to nanometer spacing. Then it might not be feasible to have a geometry with the size of 80 times 100 millimeter. So I believe that now it's possible to go with the smaller pore sizes.
Okay, thank you. There is one more question. from Hosseini Nasab. Where was the application of the study?
So this study is, I would say, a fundamental study. And the motivation was for, as I mentioned, subsurface applications. In specific, as Kathleen also discussed, for enhanced geothermal system, which is a fractured porous media. But we believe that our measurements can be used to elevate our understanding of any other porous scale industry. So whenever we are dealing with fractured porous media, these measurements can be used to shed light on our understanding.
Thank you very much. Then I would say, there are no more questions. Then I would say we go to our next talk. Thanks again for Mehrdad for the nice presentation.
Yes, thank you.
The next speaker is Tapomoy Bhattacharjee, and he is a postdoctoral fellow at Princeton University, mentored by Professor Sujit Datta. He completed his undergrad studies at Jadavpur University, India, and conducted his graduate work at the University of Florida, for which he received the award for outstanding doctoral thesis research in biological physics by the American Physical Society. Currently, he focuses on the understanding and controlling the behavior of bacterial populations. The floor is yours. You're muted.
Hi, I'm Tapa. My name is Tapomoy. I go by Tapa. I'm a postdoc here at Princeton, and today I'll tell you about bacterial motility in porous media. This work is mainly done at Professor Sujit Datta's lab with Daniel and Jenna, both are grad students who focus on modeling bacterial chemotaxis in porous media. So when we start talking about bacteria, we are talking about something that we are studying for past 400 years. Leeuwenhoek first reported about bacteria about in 1678 or something. So what that means is that over this large amount of time, what we have studied bacteria mainly in homogeneous materials, in liquid culture, in surface of soft agar substrates. These are all homogeneous material. But if you think about the places where bacteria live, the many physiological irrelevant situation and environmentally relevant situation, bacteria live in complex porous environment. For example, they live in our gut mucus, in our intertissue pores. In environment, they live in soil and sediments, subsurface formations. These are all complex porous environment. So, for example, if you want to model how an infection spread through tissues, or you want to develop an effective bioremediation strategy where a population of bacteria will effectively navigate through soil and degrade a pollutant, the first thing we need to know how these bacteria are moving through such complex porous environment. Today, I'll tell you what we are doing to solve this problem, because mainly it is extremely hard to know how these bacteria move through the spore space, and that is due to the opaque nature of any porous media. So you cannot experimentally measure how they can diffuse through the system, what the bacterial flux is, and how pore scale confinement sets those. So what we have done, we have created transparent porous media by simply taking some hydrogel particles, swelling them in bacterial food so bacteria can live happily in this porous media. And we pack them really close to each other. Now, bacteria can live inside this material, and they can also migrate between the interhydrogel pore space. You can use a tracer particle, let the tracer particle move inside the pore space, and you can image the overall structure of the pore, and you can see the pore space is really tortuous. You can even track those tracer particles to measure the pore sizes, and we found the pore sizes are exponentially distributed, much similar to any random porous media. So now we have a porous media where we can disperse cells and we can measure the pore size. So the first thing we did, we dispersed bacteria and measured how they move inside this material. And when we did so, we were completely blown away, because it doesn't look like the cells are doing this traditional run and tumble motion that is universally assumed for bacteria in homogeneous material. Instead, these cells get trapped into this tight pore space inside this porous medium. They constantly reorient their body. eventually they find a directed pathway where they can hop to the next trap. So they are hopping between traps. And what sense is this hopping and trapping? Turns out hops are set by pore space geometry. Cells hop when they find a directed pathway in the pore space. However, traps are set by both pore scale confinement and cellular activity. And we can model the system by considering these traps or entropic traps. Now we can measure the hops and traps separately. What we are proposing is the long-term diffusivity of bacteria is not given by their run and tumble motion anymore. It should be given by the hop length squared over trap time, because hops are when cells make most of the move and traps are when they spend most of the time. And finally, what we did is we injected a bolus of bacteria inside our porous medium and measured their macroscopic diffusivity. We have also predicted a diffusivity from our measured hop length and measured trap time. And we find that our measured diffusivity matches with our predicted diffusivity within a factor of 3. So what that means is we can predict the long-term diffusivity of bacteria just by watching single cell motion in 3 dimension. Now the question is, how relevant is this? Because bacteria live as a population in porous media. Yes, they do also live as a single cell. Single cell diffusivity are important, but you also need to know what sets the bacterial flux inside porous medium. But how would you possibly create a dense population of bacteria deep inside porous media with the right size, right shape, and the right aspect ratio? That's a really tough job, right? Turns out, since our porous medium do have some self-filling material property, we can 3D print inside this porous medium. And during my doctoral work, I have developed this 3D printing process where you can create any structure of any material inside this kind of porous medium. And you can create similar structures with bacteria directly. And we start by making a cylinder of bacteria. If you look here, this cylinder is embedded inside a porous medium, and you are actually looking at it from the top down. Each individual pixel here represents one bacterium. This overall field of view is about thousands of cell lengths. So if we watch it over time, I was expecting that these cells will basically diffuse, they will cover up the whole field of view, but instead when we watched it, we found this. They're forming beautiful traveling waves. Let me remind you here, each individual pixel is a bacterium here. So these bacteria are moving thousands of their body lengths collectively through this pore space. And you must be thinking, okay, since this process happens over about 15 hours, these cells are not actually motile. They're probably pushing their progenies forward. But if you zoom in one of those traveling waves, you'll see the cells are actually motile. They're moving in random direction. However, the front moves at a constant speed at a constant direction, and the front speed is pretty low. And since we are collecting this data on a confocal microscope, we can see this process from side and confirm that it's truly a one-dimensional problem where a solid cylinder of bacteria expand as a hollow cylindrical shell. And we can collect this data, and we can azimuthally average this fluorescent intensity to question how fast these traveling waves are moving. And in fact, if we repeat this process at different pore sizes, we can change the pore size. So we can repeat this process at different pore sizes, and we find that as we decrease the pore size, the traveling wave speed decreases. So what sets this traveling wave? Why do they form? Bacteria are much like us, much like human. We go to a place, we deplete the place out of its natural resources, and then we complain about it and we want to go to Mars. And similarly, bacteria are nothing different. So once we create this green population of bacteria, which is embedded inside this porous medium filled with orange nutrients, they start to eat their nutrients around them, and they eventually set up their own nutrient gradient and chemotax towards their own nutrient gradient. So they're chemotaxing their own nutrient gradient here. And since there is a clear separation between of time and length scale between individual cell motion and the motion of the traveling waves, we can use a continuum scale formulation like a Killer-Segal type reaction diffusion model to model our system. And unlike traditional modeling, here we are using our measured diffusivity in the system, and so we can question their chemotactic traveling speed and chemotactic parameters. And we found that our reaction diffusion model qualitatively predicts the traveling wave formation. And if we repeat this process at 3 different port sizes, we find that not only this modeling predicts this traveling wave formation, it also shows that this traveling wave is actually following the nutrient gradient. And finally, since we are imposing this measured diffusivity in our model, we can question the chemotactic parameter or the chemotactic sensitivity of this bacteria in porous media. Traditionally, this is thought to be an intrinsic parameter of bacteria, intrinsic property of bacteria, which you found that in porous media, chemotactic parameter is also pore size dependent. And finally, I want to talk to you about this movie one more time. If you look at this, the general question that comes to mind, how this seemingly random motion form this beautiful traveling waves. In other words, how chemotaxis even happening in porous media. And surely we didn't discover chemotaxis, but chemotaxis is known for years, and people have found that E. coli cells can chemotax towards a more nutrient-rich zone by simply elongating their runs towards a more nutrient-rich zone. Can this happen in porous media? Can they elongate their hops? Our prediction is no, because hops are set by pore space geometry, so they cannot hop longer than the space available to them. And you might argue that they can truncate their hops in the opposite direction of the nutrient. And we think that is also not possible because we have found that confinement suppress flagellar unbundling, so cells cannot stop their hop halfway through. And to verify this, we have tracked individual cells at the leading edge of this propagating waves, measured their hop lengths, and we found no directional bias of the hop length. So how these cells are actually chemotaxing? There exists another mechanism by which E. coli cells can chemotax in homogeneous liquid material. They can move towards the more nutrient-rich zone by biasing their reorientation amplitude. So when they reorient more towards the nutrient-rich zone. Out, cells can actually do this by controlling the number of flagella that are involved in the unbundling process. We think since cells cannot elongate, is probably the dominant. And to verify this, we measured the probability density of hopping at different direction, and you find that indeed cells are more probable to hop towards a more nutrient-rich zone. And to verify the relative contribution of these two mechanisms, we have measured the chemotactic front speed from the individual cell motion. And in this equation, if we replace the directionally dependent hop length by an average value, it does not change the overall front speed. However, if we replace the directional bias of the hopping by a uniform distribution, that completely changes the chemotactic front speed, which confirms that this secondary mechanism of chemotaxis is the dominant mechanism of chemotaxis in porous media. So what we have found here, we found a new form of motility, which is hopping trapping motility, which is controlled by pore scale confinement and cellular activity. And we found that measuring hopping lengths and trapping duration, we can measure the long-term diffusivity. And we have found that confinement regulates, but do not suppress the chemotaxis. And chemotaxis in porous media occur by anisotropic orientation of cells. And with that, I would like to say thank you, and I would love to take your questions.
Thank you for a very interesting talk with some fantastic videos, Tapa. If anyone has any questions, please write them in the comment section and I shall ask them. I had a question. So you had the predicted diffusivity at the beginning, and for this work you did it with just one fluid in the porous medium, right, for the bacteria to live in? Do you think it would be heavily impacted if you had a second fluid? And how much do you think that would affect your estimate?
How would you, so what if I had?
If you had, say, like another fluid in the porous medium,
So there are a lot of
live in.
studies that is the extensive studies on like how viscous fluid change bacterial swimming, bacterial behavior. Here we just wanted to see the effect of confinement. So the porous media is filled with like liquid. It's basically water. It's water filled with like bunch of salts. Now, to your point, if we replace it with some viscous fluid, like some polymer solution or glycerol or like, some other viscous fluid, then you have to couple the effect of the viscosity. But in other words, it only depends on how, it's going to change their trapping time. You have to think like, cells are moving as fast as they can during their hops. That might also slow down. So you have to now take into account of like what the hopping time matters in the diffusivity calculation. So in other words, you have to kind of like incorporate and see like how important is hopping time relative to the trapping time.
And if you say had water and air in your porous medium, do you think that would inhibit the direction more so?
Yeah, that's a very interesting thought. I mean, a real porous media, real soil do have some air trapped in those things, right? And currently we are actually exploring that part, is basically like trying to understand like how they navigate confinement and an air-water interface simultaneously. And people have done that, and people have shown that like cells accumulate at certain locations, but how individual cell motion get altered, like in those kind of environment experimentally, it's a little bit challenging, but I think we are going to find out pretty soon.
Oh, that's interesting. We have some questions now. So the first one is, was there any stochastic modeling for this hopping?
Yeah. So I mentioned that we are modeling the trapping time as like entropic traps. I had just skimmed through the whole thing, but it's very simply, we are thinking that these particles, these cells are trapped into a pore space. There are many avenues they can take to get out of this trap. So you can think of, there are bunch of configurations that this bacteria can take over time. Some of this configuration will take them out of the pore space, and some of these configurations will keep them trapped in the pore space. And if you think that this is kind of given like an Arrhenius kind of process, you can measure, you can get a trap time which should be power law distributed. And when we measure our trap time distribution of the cells, or the duration of the cell spin in a trap, and make a probability density distribution, we find those are also like power law distributed. So that's how we are saying that the competition between confinement and cellular activity kind of controls this this trapping process in porous media.
Okay, thank you. There's another question, which is the observed diffusivity of bacteria in porous media lower compared to the diffusivity of bacteria in the pure liquid?
Absolutely, yes. It's lower by almost like a factor of 50 or more. So traditionally it's thought that diffusivity is given by the run length, how much they can run, over run time, run length squared over run time. Now, if you think about that, run lengths are order of like 60 micron over like few milliseconds. A few seconds, and then you measured the diffusivities order of magnitude higher than what we measured in porous medium. And usually it has been thought that cells still do move by run and tumble motion, but their run lengths get shorter by constant interaction with the obstacles inside porous media. So if you want to measure the diffusivity should be given by shortened run length and the run time. And we found that if you make that assumption, the diffusivity you would predict in porous medium are also like an order of magnitude higher than what we have measured. because like cells are not moving by run and tumble, they get constantly trapped in the pore space. They have to constantly rearrange their body. They have to constantly find a directed hallway that they can move and find the next trap.
Okay, thank you. I feel like Kamal, you want to ask a question?
Thank you very much, Tapo, for this fantastic talk, first of all.
Yeah,
Really
thank you.
fantastic. Really enjoyed it. I've got a couple of general questions. They are more naive because I'm not from this field, to be honest. Uh, uh, in real porous media, although it's going to be difficult to visualize these things, if you have some clay particles, and what do you think is going to affect the migration or the collective behavior? Uh, any effects of clay and the charging of the clay on it on the movements?
Uh-huh. So yes, and there is always like charge interaction that might happen with the bacteria and the clay particles. That is possible because if your particles are positively charged, bacterial wall is negatively charged, there will be a Coulombic interaction there. So to avoid this, for now, we just wanted to find the effect of confinement. We want to separate the effect of confinement from any other contributors. And we found that, so our particle also do have a charge on the surface. Instead, being positive, our particles are negatively charged. These are made from negatively charged polyelectrolyte. So bacteria do not have like a attractive interaction between the particles and bacteria. But you are absolutely right. If you have like another Coulombic interaction, then you have to add an effect of like how these bacteria get trapped on a surface, not even in a confinement. They get like attracted to the surface and remain trapped. But it's basically the same idea that they are moving and they get trapped. And you can think of what drives this trapping. Either it is driven by the confinement, or it can be driven by a surface interaction. But in the overall, like the physical model of like there is a short, fast motion, and then followed by a long trap is I think is still going to be there.
Just one quick one. If you have another dimension of temperature on it, what's the effect on diffusivity and things like this could happen?
Yeah, that's a very interesting question. We actually did that work I didn't show it here. So what happens is that as you lower and lower, so like I mentioned, actually, let me see if I can go back to that slide. I don't know if the slide is still up. But so I'm trying to go back to this like trapping model thing that we are talking about. So we have verified this. So here we are saying it's a competition between your confinement, which is C here, and activity, which is X here. So as you lower the temperature, since our porous media is athermal, so there is not much significant difference in the pore size or the pore size distribution. So the confinement remains the same, but you change the activity because the swimming speeds start to change as you lower the temperature. And their metabolic activities start to change. So when you change the activity, your bacteria get trapped way longer compared to when you have the cells dispersed at regular room temperature. So your diffusivity start to decrease a little bit because of the temperature being increased and the activity being, so you're trapping things for a longer time. And since your diffusivity is given by the Hopland square of trap time, the Hopland changes a little bit too, but sorry, the Hopland doesn't change. Excuse me, because the Hoplands are pore space dependent, and you do not change the pore space, but your trap time changes a little bit too because of the activity. So your diffusivity start to go down.
Oh, thank you very much. Yeah, I think it reminds me of one thing. when you have drainage process, things can happen from throat and they jump straight where there's no point of like they can stop in between. But that's a different subject. Yeah, it just reminds me of similarity between this bacterial motion and our drainage processes. Thank you, thank you very much.
Yeah, this kind of like hopping and trapping happens in a lot of systems. One thing that can jumps out is like electron moving through like different disordered energy landscape and stuff like that. And the same kind of argument holds there too.
Awesome.
Okay.
Thank you.
Great. So thank you again, Tapa. We are running out of time, so I shall wrap up the session. This is the end of our talks in 2020. So we will see you in 2021 when we resume with our Brazilian special. So stay safe until then, and we will see you all on the 26th of January 2021. Yeah. Bye, everyone.
Bye.